In the last video, we talked about exactly what radio waves are and some basic concepts. In this one, I'll go over the parts of a simple radio and how to build one. Any radio, or more specifically radio receiver, no matter how complicated, can be broken into simple sections. More complex radios obviously have more sections. The simplest receiver you can build has just 4. These are the antenna ground system, here abbreviated as AG system, which collects the radio waves, the tuner, which tunes to the right station, the detector, which detects the information in the radio waves, and the reproducer, which turns the information into something you can hear. I'll go over each one in detail, starting with the antenna ground system. Say that you string up a piece of wire so that one end is in the air and another is connected to the ground. When radio waves hit the wire, they set up a voltage, or electrical pressure, along it. This causes a small electrical current to flow down the wire into the ground. Because the radio wave is a wave, the current soon stops before reversing itself, going up the wire from the ground. It then speeds up before reaching its maximum speed, slows, stops, and reverses again. Then again, and again. All this happens at the frequency of the radio wave. In simple terms, what happens is that the radio wave is captured by the wire and causes current to flow along it. The wire connected to the ground is our antenna ground system. The part in the air is called the antenna, while the part connected to the ground is grounded. Every radio needs to have a way to tune to only one station, otherwise you would hear every station at once. This is done through the tuner, which uses what is called resonance. Resonance is, particularly in electronics, is a little tough to understand, but I'll try my best to explain it. Set up a row of glasses, each with a different size and shape, on a table. If you tap each one with a pencil, each glass gives off a different tone. What's happening is that tapping the glass causes the glass to vibrate, creating airwaves which, when they reach your ears, are heard as sound. The reason each glass has a different tone is because each of the airwaves, or sound waves, has a different frequency, which is caused by the glasses vibrating at different frequencies. The frequency an object will vibrate at is determined by its material, shape, size, and thickness. It is called the natural frequency of the object. An object will also vibrate if sound waves of its natural frequency hit it. If this happens, it is said that the frequency which hit it and the object are in resonance. It will vibrate only if sound waves of that frequency, not any other frequency, hit it. The same thing applies to the radio. We need the receiver, more specifically the receiver's electronics, to be resonant at the same frequency as the radio station we want to receive. However, this does not involve sound waves, but electrical waves, more specifically, radio waves. Now that we have recovered the information, we need to turn it from electricity into sound. This is done by the reproducer, which is essentially a speaker. However, in our case, we'll use an earphone. Finally, you might think that we could just listen to the radio right now, but remember how I mentioned in a previous video that the information we are trying to hear, whether it's speech or music, is encoded within the radio wave. More precisely, it is modulating the radio wave. The information is controlling the radio wave. To be able to listen to the radio, we need to demodulate the signal to recover the information. In other words, we need to turn the radio wave into something that we can hear, some sort of signal like the sound of speech or music. This is done through a detector, which detects the information. The input is the modulated radio wave, while the output is the information. Now let's take what we've learned and use it to build a simple AM radio. Along the way, I'll make a circuit diagram, or a simple drawing showing what the electronic circuit looks like to help. You'll need a lot of wire for this project. Let's start with the antenna, which is represented by this symbol. For the antenna, you want to use a long, straight piece of wire. For mine, I used about 15 feet, but I do live relatively close to a station, so it's easier to receive. For optimal reception, your antenna should be about 75 feet long and should be as high above the ground as is practical. It should be kept away from any obstructions, particularly metal ones, and should have insulators, materials that do not conduct electricity, such as rubber, attached to its end to prevent the current you are trying to capture from leaking off. The antenna is connected to the radio set via a lead-in wire, which ideally should be part of the antenna wire itself. This lead-in wire goes from the antenna to the radio. If the antenna is outside, it goes through a window if necessary. If the lead-in wire is not part of the antenna wire, it is necessary to strip the insulation from the ends of both wires and either twist them together or solder them together. Now it's time to create the ground connection. Note the symbol for ground. You don't have to connect the radio to the earth itself. Just take a wire, not the lead-in or antenna wires, and connect it to a metal cold water pipe or any other metal pipe which goes into the ground. Never use a gas pipe. The wire, with the insulation stripped off its end, should be connected to the metal of the pipe. An alternate method is to wrap the bare end of the wire around the grounding plug of an electrical plug and plug it into an outlet. Be very careful that you are plugging the wire into the grounding plug. Do not connect the ground wire and the lead-in/antenna wire yet. We are going to put something between them. That something is the tuner. The tuner consists of 2 parts, an inductor and a capacitor. Let's look at the inductor first. An inductor is a coil of wire wrapped around a tube. It's not the best drawing, but you probably get the point. The inductor, when current flows through it, produces an electrical effect called inductance. The amount of inductance the inductor produces depends on 4 things: the number of turns or loops of wire, the length of the coil, the core of the coil, the core is the material which is inside the tube. The most common coils are air and iron, with air coils being the most common for the tuner, and last but not least, the diameter of the tube. The unit for inductance is the Henry, abbreviated as H, and inductors have the following symbols. This is a symbol for an air coil core inductor, and this is a symbol for an iron core inductor. We can change the inductance by varying the number of turns, the length of the coil, the core of the coil, or the diameter of the tube. Variable inductors have the following symbols. That, or that. When we want to represent inductance or an inductor, we use the letter L. Let's add an inductor to our circuit here. The filled in dots represent when 2 wires connect. The second part of the tuner is the capacitor, which is 2 or more metal plates facing one another which are separated by something, called a dielectric. The dielectric will not conduct electricity. When current flows through the capacitor, it produces an effect called capacitance. Capacitance depends on 1. The thickness of the dielectric, or the distance between the plates, 2. The total area of the plates, and 3. The material of the dielectric. The unit for capacitance is the farad, or capital F. For our purposes, we usually use the microfarad, or UF, which is 1 millionth of a farad, or the picofarad, or PF, which is 1 trillionth of a farad. The symbol for the capacitor is this. Like the inductor, we can change capacitance by changing one of the 3 factors which determine capacitance. The most common method is to change the area of the plates by making one set rotary, or making it so you can turn it, and the other set stationary. As you turn the plates, the area of the plates facing each other increases, increasing the capacitance. The symbol for a variable capacitor is this. When you want to represent capacitance or capacitor, we use the letter C. If you connect an inductor and a capacitor, you make a tuning circuit. When you apply a voltage or electrical pressure across the coil over the capacitor, an electrical current will flow back and forth through the tuning circuit. This back and forth is called oscillation. The natural frequency of the oscillations is determined by the product of the inductance or capacitance, or L times C. More precisely, the frequency, or F, was 1 over 2 pi square root LC. If the frequency of the oscillations equals the frequency of the radio station, then your tuning circuit will be in resonance, or in tune, with the station, and will receive only that station. To let one tune to multiple stations, a variable capacitor is normally used. Let's add a variable capacitor to our tuning circuit to finish it off. The first step to building a tuner is to make the inductor. Start by choosing a thing to wrap their wire around. It should be hollow, such as this paper towel tube, but it doesn't have to be a cylinder. As you can see, mine right here is a rectangular prism. Now you need to make an inductor with the inductance of about 230 microhenries, or 230 millionths of a henry. If this sounds daunting, don't worry. There are online calculators where you can plug in the amount of turns you'll be doing, the diameter of the wire, and the area of the thing you are wrapping the tube around to get the inductance of the inductor. The one that I used, which can be seen here, is linked in the description. Again, if you want an inductance of about 230 microhenries, the weird-looking U is the Greek letter mu and means micro. Leave some wire both before and after your coil and take the insulation off its ends. This is where you'll connect the inductor to the other components of your radio. Now it's time to create a capacitor. Ideally, you would get a capacitor from an old radio, but it's likely that you don't have access to that. Instead, you'll need to create one yourself. Cut 2 6" by 6" square pieces of aluminum foil and 1 7" by 7" piece of paper. Using masking tape, tape one of the pieces of foil around a paper towel tube and tape the other foil piece to the center of the paper. Wrap the paper and the foil around the paper towel tube and tape it so that it stays wrapped around it. Then, take 2 pieces of wire without insulation at their ends and tape them to the capacitor, one on each piece of foil. The end result should look like this. Now that we've assembled the capacitor and inductor, it's time to move on to the reproducer. For our radio, we use a special earphone and it is a high impedance earphone. The earphone works through magnetism. Just take a regular iron rod, wrap a wire around it, run current through the wire, it will become magnetic. This is called an electromagnet, and it is the basic device that makes speakers work. If you open up the earphone, which I do not recommend doing, you find an electromagnet inside. Separating it from the outside of the speaker is a diaphragm, which is a thin iron disc. If a current is run through the electromagnetic wire, it will become magnetic and pull the diaphragm. If the current varies, the pull in the diaphragm will vary and will go in and out, producing a sound wave that we can hear. Loudspeakers work in the same way, but they have a stiff wire, which connects the diaphragm to a paper cone. As the diaphragm moves, the paper cone also moves, putting a larger amount of air in motion and producing a louder sound wave. These are the symbols for earphones and a loudspeaker. Recognize this one? You've probably seen it before. And here is the radio with the earphones. Now we have what appears to be complete radio. However, if you build a radio like this and put the earphone in your ear, you will hear nothing. Why is this? To understand why, you have to know just what electricity is. An electric current is a movement of many negatively charged electrons. Although they only move short distances, the current travels through the wire at great speeds, similar to the waves discussed in the previous videos. When the current flows in only one direction through the wire, it is called direct current, or DC. If it flows in one direction, then goes in the other direction, and then reverses itself again and again, it's called alternating current, or AC. Like other kinds of waves, AC has a frequency. One example of this AC is the AC used to power your home. This AC has a frequency of 60 Hz. Remember, a Hertz is a cycle per second. Another example is a current in the antenna ground system. This current has the same frequency as the radio wave which hits the antenna, that is, it is at radio frequency, or RF. Right now, that RF alternating current is what is applied to the earphone, and that is why you would not hear anything if you built the radio right now. For one short instant, the current applied to the electromagnet in the earphone pulls the diaphragm one way, but in the next instant it switches direction and pushes the diaphragm the other way. The diaphragm is not sensitive enough to follow this pushing and pulling, so it stays still, and there is no sound. How do we make the radio work? We need to somehow stop the current from going back and forth so that the diaphragm can actually move. In essence, an electrical gate is needed that can only let the current flow one way. This way, when the AC moves in one direction, the gate will let it through, but when it reverses, the gate will block it. It will turn the AC into DC, particularly pulsating DC, because it will consist of a series of pulses. In the late 1800s or early 1900s, it was discovered that some crystals, like galena, a type of lead ore, could conduct electric current in one way but not in the other way. Such a crystal is the basis for the first major type of gate, or detector, to have been developed, a cat whisker detector. One wire is connected to the crystal, one other wire is connected to the cat whisker. A thin wire, which lightly touches the crystal. Electric current can flow freely from the crystal to the cat whisker, but not in the opposite direction. When this current is applied to the earphone, it causes the diaphragm to move in and out in a way that produces sound. Here's a symbol for the crystal detector. If you're like me, you probably don't have easy access to a crystal detector. However, don't panic. Instead, you can use what is called a diode, an electronic component which does essentially the same thing. You want to use either a germanium diode or a Schottky diode. Both of these are more sensitive than silicon ones, which should not be used in the radio, at least not right now. So, with that in mind, here is a diagram for the completed radio. This radio is called a crystal radio. It has a name due to how it relies on a crystal detector to produce sound. Here's my modern day version of the crystal radio. You don't need a fancy electronics board, I just use that to connect the wires together. You might notice I never talked about batteries running either current and power supply. That's because this radio doesn't need any. All the power it needs comes from the radio waves it picks up. It does have the disadvantage of being very quiet as a result, however. Thanks for watching. Stay tuned for part 2, in which we'll go over some more information on the crystal radio and in which I'll talk about a way to improve it.